on this computer? Okay, we're recording. We're good.
Pick up Jordan up.
Say the ayes.
My sister is doing optimization for aeronautical engineering and space ships.
That's cool.
That means that's so many.
I agree.
I didn't have a sister.
Okay.
No, you're right.
3.7 through 27.
This is wrong.
7. Here we go.
When is India? It's the real question.
Oops, to the meter.
Now, again. So, optimization. We're not doing any new math. We're basically taking all the calculus that we've been using, kind of like in 3.6, the curve sketching. We're taking all of that, everything we've just done, and we're applying it to kind of simple word problem, real life situations. So optimization is a useful application of differential calculus. All that means is it's an application of derivatives, right? We've been studying derivatives. This is a type of application of derivative. Anytime you're trying to find the largest, smallest value of something, you are trying to optimize. There's usually some sort of constraint keeping a quantity from getting infinitely larger, infinitely small, and we'll discuss what those are in the following situations. Here are my steps for solving optimization problems. Now, first step, read the problem carefully. Now, often, anytime you are solving an optimization problem, you are identifying either the absolute maximum or absolute minimum. However, the wording of the question may not say what is the absolute maximum or the absolute minimum of this function. Words like maximize, maybe maximum is used, maximize, find the largest value, find the fastest time. Like those types of words might be used, and you need to read the problem and interpret what is being asked of you. But for all of these problems, you are being asked to find either an absolute maximum or an absolute minimum. Arjun.
It's like linear programming.
Also used for optimization, but this is using calculus. Okay. Now, if possible, draw, so similar to like related rates problems, I suggest drawing a picture if possible and labeling it with the variables you want to use. State what you were trying to optimize and write what I call an optimization equation for the quantity. So for example, if you were trying to maximize volume, you need a volume equation. That will be your optimization equation. If you are trying to minimize cost, you will have a cost equation. The issue is that your equation, your optimization equation, Simon, might have multiple variables in it. So you don't know how to differentiate that. You will sometimes need to come up with a secondary equation. So an equation that you can come up with from the given information and use that secondary equation to rewrite your optimization equation in a single variable. Once you have your simplified optimization equation, then you want to take the derivative of your optimization equation so that you can identify critical numbers or critical values for the function, the optimization function. Remember, whether you are finding absolute extrema using the implications of the extreme value theorem, or you are using like first derivative tests to find relative extrema, you always need to know what the critical numbers are for the function over whatever interval it is you're working on. I also suggest stating the domain of your optimization equation. It's really nice whenever you are able to define your optimization equation on a closed interval, knowing that your optimization equation is continuous, because what would apply if your function is continuous and defined on a closed interval?
Yes.
So I like where you're at that. Not mean value theorem, that would also require differentiable and that wouldn't really help with the optimization. But in the case that the function is continuous on a closed interval, you are guaranteed to have both an absolute minimum and an absolute maximum. That's what extreme value theorem says. So when extreme value theorem applies, you can use its implications in order to then consider endpoints, consider critical values on the interval, the closed interval, and see what gives you the largest function value or the smallest function value, whatever it is that you're looking for. That ends up being your justification. However, you're not always able to define your optimization equation over a closed interval. When you define your optimization equation over an open interval, then you have to rely on the first derivative test or the second derivative test. And you should be like, well, wait, the first derivative test is to identify what?
First derivative.
Relative extrema, not absolute extrema. However, through your interpretation of the first derivative test, you will be identifying where absolute extrema occur. You'll see that how that works through our examples. But it's really nice whenever we can use the implications of the extreme value theorem and just make that table of values. That table of values, the College Board refers to as the candidates test. So I don't, if any of you guys watch like any of the videos or anything on College Board, they refer to that as the candidates test. You need to make sure that if you do use the first or second derivative test, that you are interpreting your analysis line. And then you're answering in a complete sentence with the appropriate units. So we're going to start pretty simple here. What? Okay, our first example. Two positive numbers have a product of 192.
X times 1.
So I'm going to say, yeah, I'm going to use X times Y. You can use A times B if you want, doesn't matter. But also X and Y are positive. So we could say that X is greater than 0 and Y is greater than 0. Now the sum of the first number plus 3 times the second number is a minimum. The sum is a minimum. So I'm going to use another variable to represent the sum. I'm going to use S. S is equal to the first number plus 3 times the second number. You might be having like deja vu back to maybe algebra 1 where you had to, remember when like that was really tough, where you had to interpret, like write an expression that represented a given statement. Now, this sum is a minimum, which means we are trying to minimize S. That means that S equals to X plus 3Y is our optimization equation, but we can't differentiate yet. Why can't we differentiate? Why can't we find the derivative of S yet?
I don't know the derivative of X.
Two variables, but we do have this secondary equation. This is our secondary equation that we can use to rewrite our equation for X. So we could solve for X or Y. What do you guys want to solve for X or Y? Y equals 192 over X. So we can rewrite
X plus 3 times 192 over X.
right. So 3 times 192 is 576.
Yes, I got it off the top of my head.
might want to rewrite that like so, since we're going to find the derivative. But this is our optimization equation.
What do you mean by that? What is an optimization equation?
It's the equation that has the quantity that you are trying to optimize. We are trying to minimize the sum, S. So that's the equation we're going to take the derivative of, meaning that's our optimization equation.
Whatever value is to make us.
We're trying to find the value of X that would make S the smallest value possible. So that's why that's our optimization equation. X times Y equals to 192. That's our secondary equation because the quantity that we are trying to minimize is not in that equation.
That says optimization.
Q for equation. So S prime is 1 minus 576 times X to the negative second. Now I would rewrite this with a common denominator.
Whoa.
Because think about what we're doing. Why don't I keep writing the 7 first? Think about what we're trying to do. We're trying to find critical numbers. Sigh. That's a big sigh.
What's the square root of 576?
What is the square root of 576?
18.
27. Okay,
Do you guys have calculators?
It-
You should.
I got this, it's gotta be. I think it's 34.
I think it's actually 24. I was just making the illusion it's fine.
I mean, I think it's 24. That's what I got.
That's what I did in my brain actually, yeah. Why did you write it before we could say that?
Sorry,
My love of learning has been focused.
I've crushed your love of learning. All right. So those are the potential critical numbers. However, we can throw one of these values out. Which value can we throw out?
Negative 24, because that has to be positive.
X has to be positive. Now, 0 we would also consider as a possible critical number because that would make S prime undefined, but 0 would make S undefined, and 0, we were given that X has to be strictly greater than 0.
Precisely 24. We know that.
Now our optimization equation is defined on an open interval for X greater than 0. So let's use the first derivative test, which I know is for relative extrema, but our interpretation will allow us to identify the absolute extrema. So this analysis line is for S prime, and I'm putting 24 critical number on the analysis line. Thinking about plugging test values in, we would go from negative to positive for S prime. So S goes from decreasing to increasing.
Holy. Positive relative.
Relative, right? That's what first derivative test is for. However, if we think about this says that the graph of S from 0 to infinity goes from decreasing and then changes to increasing at 24. And then is increasing forever. So will there be another low point on the graph?
No.
No. So at X equals to 24, that's going to minimize the sum. That'll end up being the location of the absolute minimum. So we need Y. We can find Y by plugging 24 into our equation for Y, which was up here, right? 192 divided by 24 is 8. Okay, 3 steps here. we need to make a statement that summarizes. And then for our justification, we need to make a statement about 24 being a critical number and the sign change in S prime on the interval for X greater than 0.
Do you also need to justify absolute most of that?
No, that's how we're doing, like it's implied that because that's our only critical number, it's gonna end up being the absolute minimum, right? So
But we don't.
first to summarize, what?
We have to justify. It just asks.
Yeah.
what are the two-
Yes, you do, because, and okay. An analysis line in a free response will not be graded. You have to interpret the analysis
So
line.
if you don't have to justify.
However, optimization problems are usually going to come up as multiple choice questions. So you don't have to justify,
Yeah, it's okay.
but if you did have to justify, I'm going to show you how you would do that. Okay,
Yes, so you don't have to, yeah.
and if you took calculus last year, this is, remember these problems? I was like, the analysis line is fine for now as your proof or your justification, but in AP, you have to do the extra step of interpreting. So we can say something like the two numbers are X equals to 24 and Y equals to 8. Because you would say something like S prime of 24 is equal to 0 and S prime changes from negative to positive on the interval X greater than 0. Kind of ends up being like step 1, step 2, step 3. This interpretation only has to be done when you're using the first derivative test. If extreme value theorem applies, like where you're able to do the table, that is your work. That is your justification for the maximum or minimum, the absolute maximum or minimum. Any other questions on this problem? Okie dokie. Any Yellowstone fans in here? I guess not. Maybe it's like an old person. Is it an old person show?
It's just not streaming anywhere that I would like see this.
It's true. It's on there.
It's a really popular show, but.
It's like
actually we don't-
The Montana version of The Sopranos.
Well, I thought you meant like the national, so.
Well, the national park is in there, but it's
That's what I meant.
Yellowstone Ranch. There's, but anyways, it's a really good show. I think it's a really good show. It's maybe an older person show. I don't know. Kevin Costner, probably an older person show. Field of Dreams? No?
That's just kidding.
I like that. Okay, anyways, I'm just showing my age now. So John Dutton plans to fence a rectangular pasture adjacent to a river to keep out wolves from the national park. The pasture must contain 180,000 square meters in order to provide enough grass for his herd of cattle. What dimensions would require, oops, typo, the least amount of fencing?
No.
What can you talk about?
Could you? No. No. But there is one on here that we're gonna do that you technically, you could use algebra. Okay. So let's draw a picture first. Here's the river.
There's a lot of daisies in Yellowstone National Park.
A lot of daisies.
Also, the wolf population in Yellowstone National Park was endangered in that. Because there was nothing. And then there was like,
He's on Google.
yeah, there was, I think it was.
So the area of this pasture must be 180,000 square meters. I'm going to call the sides that are parallel to each other here, X, and then the side that is parallel to the water, I'm going to call Y. Remember, it's important that you stay consistent with however you've labeled it. You could label it, use different variables than me, up to you. What are we trying to optimize here?
Minimum X, 2X plus 2Y.
Just in words, without the equation. We want to use the least amount of fencing, which for what Simon was saying, that means we want to minimize the sum of all of those sides, right? I'm going to call the sum of all those sides of fencing F. For fencing, yes. So then X plus X is 2X plus Y. And we run into the same issue that we did in the previous example, where we have F is in terms of two variables. So we were trying to minimize F.
Well, we know that X times Y is 180,000.
Exactly, that ends up being our secondary equation. We know that X times Y is 180,000. So if we solve for Y in our secondary equation, we can rewrite our optimization equation in terms of X.
Is there a rule about which one you should do, which one you should replace?
No, you could do either, and you'll get the same result.
Yeah.
Now let's see, before we take the derivative of F, our optimization equation, what restrictions can we put on X? Like X, yeah, X would have to be greater than 0. And because X can't be 0, like we have no chance of defining F on a closed interval, I'm not even going to do like the mental gymnastics of trying to come up with a upper value for X. So we can just say that F is defined on the interval for X greater than 0. So we're going to have to use first derivative test again, or you can use second derivative test. Up to you. I'm going to use first derivative test. All right, so let's find F prime. That would be 180 minus 180,000 X to the negative second. We again want to get a common denominator. Does it make sense to everyone why I am doing this step of getting a common denominator to write as a single fraction? No? Okay. So the reason that I am doing this is because from the first derivative, we are trying to identify the critical numbers for the function f. Critical numbers, remember, occur wherever f prime is equal to 0 or where f prime is undefined. Okay, that's for critical numbers. As long as those x values are in the domain. When we have a fraction, when we have f prime as a fraction, we can just think about setting the numerator equal to 0 and solving for determining where f prime would be 0. And we can think about setting the denominator equal to 0 and solving for where f prime would be different.
How'd you get minus 180,000 X to the negative?
Derivative of this, right? This is 180,000 times x to the negative first.
Like load.
No, I didn't use it. I just used power rule.
Oh.
I thought of this as being 180,000 times x to the negative first. Just use power rule. Okay, so, well, f prime would be undefined at 0, but 0 is not even in the domain of f. So we only need to consider where the numerator would be equal to 0 to identify our critical numbers. So we get x squared equals to 90,000. So x is equal to plus or minus 300. However, x must have to be greater than 0 so we can ignore the negative. Again, because f is defined on an open interval, we have to do the first derivative test. Or the second derivative test, but I don't want to find the second derivative. Yeah. You can use the second derivative test, especially if your critical numbers only come from where the first derivative is equal to 0, but I think it's easier to just use first derivative. So this is for analysis line is for f prime. I'm putting 300 on the analysis line. Did I see a hand up over there? Arjun.
If you had like multiple relative means, would you have to test, like plug it into the original function to see which one is more minimal?
Oh, yeah, and do like a
Like an analysis line for two.
theoretically, but the thing is, all of these problems, it's going to end up being the critical number and the point. Okay. So then we can use test values. Plug into f prime. Goes from negative to positive. F prime goes from negative to positive at x equals to 300. So f goes from decreasing to increasing. Right. So when x is equal to 300 meters, the amount of fencing will be minimized for the same reason as that previous example. The graph of f will go from decreasing and then switch to increasing. So 300 will be, when x is 300, will be a low point on the graph of f. The location of the absolute minimum. The question is asking us for the dimensions of the fencing. So we also need y. Y would be 180,000 divided by 300. So 600 meters.
So I said,
You just need that like from without doing any of it.
yeah, no.
You were like, it's gonna be
I
300 by 600 meters.
thought, okay, you could like divide it, you could get rid of 2 zeros instead of 180 divided by 3.
Okay, so we first need to make our sentence summarizing our answer. So we could say something like, to minimize the amount of fencing used to create the pasture the fence must be 300 meters by 600 meters. Or you could say like the width must be 300 meters and the length 600 meters.
Oh, how do you know?
Because what?
How do you know it's the width?
The width is shorter than the length. The length is longer. Right? The length, when we're talking with length,
No.
the length is the longer side.
I mean, what do you more? But you're like. Long.
Okay, because And we could say, f prime of 300 is equal to 0 and f prime changes from negative to positive at x equals to 300 meters on the interval x greater than 0. Arjun? You sure? How much time do you have left? Time has stood still.
14 minutes.
Ah, okay.
13 and a half.
Perfect. Okay. So both of these examples, we had to use the first derivative test. We had to interpret the analysis line that we drew. This next problem, which Christian, Sophia, I'm sure you guys recognize this type of problem. Every calculus textbook has one of these box problems, every single one. So an open top rectangular box is constructed from a 10 by 16 inch piece of cardboard. Let me draw that.
Are we including folds? Just some of the cardboard will be taken up by folding it, you know?
Okay. 16 inches, 16 inches, 10 inches, 10 inches. Okay, so an open top rectangular box is created from cutting out squares from each corner that are all the same size. So, and then cutting those squares out. So like each of these corners gets cut out. And each of these squares is the same size. So like I could say x by x, x by x, x by x, x by x, x by x. And then we fold up the tabs that are left to create our open top box. Are you referring to my box?
Why would you go box of such thin height?
Wait, like think about like wrapping boxes.
Just do everything.
And they just have to put a negative comment on.
I can't log that.
Yeah, no,
Why?
it's fine.
It's just a bunch of lines.
Yeah, like,
Bunch of lines.
oh.
We would determine the dimensions of the box that would maximize the volume. So based on the picture we started with, what would the height of the box be?
X.
10.
X. Minus 10 minus 2. 10 minus 2.
10 minus 2x would be the width. And then 16 minus 2x would be the length. Does everyone see that? You don't see it?
I do now.
Yeah.
And the volume, which we are trying to maximize, would be length times width times height. This is a rectangular prism. So x times 10 minus 2x times 16 minus 2x. Which this is kind of nice because volume, which is what we were trying to maximize, is in terms of a single variable. So we don't actually need a secondary equation this time. I am gonna multiply this out just so that I can use power rule. So that would be 160 minus 20x minus 32x plus 4x squared.
Oh, okay. No.
Okay, so this is our optimization equation. Before we find V prime and the critical numbers, let's think about the restrictions on X, so what the domain of our optimization equation is.
I think negative,
What's the smallest X?
1, like a 0, it's the limit approaching 0, I think theta.
Okay, if X is 0, what would the volume be if X is 0?
0.
Zero. Because let's think about what would happen. If X is 0, you just have your flat piece of cardboard. That's possible, right? And then as soon as you start cutting into it, then you start having volume again.
Less than 5 also.
But also less than 5, because on the shorter side here, the cardboard piece, if you're cutting 5 inches in on each side, that's going to cut the entire flap off. So then again, volume would be 0. So we can define our optimization equation on the closed interval from 0 to 5, which is nice because our optimization equation is continuous and defined on a closed interval. So we can do the candidates test where we consider the endpoints and any critical numbers that are on this interval, so the table, to see which value gives us the largest volume. Okay.
Wait, I don't know if this is like, but why is it also equal to 5? Because you have it equal to 5. It's just.
Well, it's possible, right? Volume would be 0, right? In this equation, if we plug 5 in, wouldn't volume be 0?
Yeah.
Which is
Right,
possible.
okay, so that's fair.
It would make negative volume at least.
How'd you get a 5?
I looked at the shorter side, well, Arjun looked at the shorter side. Arjun, how do you get 5?
N minus 2x has to be 3 digits.
No, that's different. It's really not the end of something.
Now it's like a little journey. So if you cut it up in here.
Okay, so our derivative, 12x squared minus 104x plus 160, we are trying to determine where v prime is equal to 0. And unfortunately, 12 is not the GCF. You could factor out the GCF, whatever it is, and then try and factor, or just go straight to your handy dandy quadratic formula. If you don't know your quadratic formula at this point, I can't help you. Sing the song.
That's like no problem.
Rachel Phillips.
Oh my God, did you guys learn it?
Too.
It's the pop good illegal.
No, that's, they're using. Oh,
It's like, it was wrong.
Alex, have you ever learned that?
You don't know your quadratic formula?
Oh, I did. Negative people are square to make around.
No song. So this ends up being 104 plus 56 divided by 12. So we get x equals to 2 or x equals to 20/3, which is too big. So not considered. So our only critical number is 2. And now we can do the table. where we determine what the volume is at the endpoints as well as 2. And we already said volume would be 0 at the endpoints. And at x equals to 2, I believe it ends up being 144. What would the units be?
Meter squared,
Hmm,
meters cubed,
What is it?
meter cubed, that's what I said.
Read the question carefully.
Cubes, inches cubed.
Inches cubed, you guys reference the question multiple times.
That's what I said. Use misheard.
Don't mistake the units. So this ends up being the absolute. Mhm. But the question is asking us for the dimensions as well as that maximum volume. So we still need the dimensions because X just represents the
Thing, whatever.
height.
Yeah,
Did you say the height thing?
yeah, that's exactly.
Okay. The width would be 10 minus 4, so 6. And the length, which is the longest side, would be 12 inches. We're not done. We need a sentence. We do. Okay, so we could say something like to maximize the volume of the box. The box must be 2 inches by 6 inches by 12 inches. The maximum volume is 144 cubic inches. You have already done the justification in considering the endpoints as well as the critical numbers. You've stated the domain of the optimization equation. You've stated the critical numbers and how you get them. So this is your justification.
Whoa.
I feel like there's not time to get through the next one. So this is where I ended with the other class. I want you to try the practice. I will post my solutions to it. You'll have that. Next class, we will go over the assignment and we will complete these last 2 examples. And then I will let you work on review for your tests on Friday.
Our test on Friday will have questions like this, right?
Yes. Yeah.
B. B. B.